or a bit of the blueprint of how the set's going to go. And then the real meat of the set builder's notation are the conditions you put on whatever's happening right here. So we're saying that the set of rational numbers are going to be those that go like some integer over or divided by some other integer, such that we follow these conditions. So these are the rules, and this is the format. These are the rules. This sentence is literally how this thing is translated. All right. So now what we're going to do, we're going to put together some examples of rational numbers. And think back, if you want, go back in the video to the set of natural numbers that I've listed before, and remember that the set of natural numbers is, sorry, the set of integers I should have been saying. We're going to be pulling from the set of integers, and remember the set of integers was 0, all those positive integers, and all those negative integers, no matter how big or how small they are. Alright? So, quite literally, I can take a 1 divided by 2. This would be a rational number. I can take a minus 3 up top and then put a 7 on the bottom. That could be a rational number. I can do a 15 up top. I could do a 5 on the bottom. That could be a rational number. However, we have to be cognizant of the fact that, listen, 15 divided by 5 or 15 over 5 is just 3 after all. So that means that the number 3 is a rational number. We can also write the number 3 as 3 over 1 if we like, which would go, with a straight connection towards this sort of P over Q situation up here. Alright? Other examples. We can have 0 over 11. Alright? 0 is an integer. It's in the set of integers. 11 is an integer. It belongs to the set of integers. 0 divided by anything is just 0. So that means that 0 is rational. Alright? And of course, well, we don't need to be doing this right now. Anything that goes like P over Q can be rational. No matter if it's a whole number, alright? No matter if it's some sort of fraction, whether it be positive or negative, it doesn't matter where the negative is. We can have a negative on the bottom. This would be a rational number as well. Alright? Anything that doesn't go like this P over Q right here, like we can't do 2.2 divided by 3. This would be wrong. We can't do negative 1/2 divided by 7. This would be wrong. Alright? Just straight up one integer over the other. Doesn't matter whether it's negative or positive. Doesn't matter if it comes out to a whole number or not. Alright? And I think I've pretty much covered all the situations where you can have rational numbers, including where you can have a whole number come out as a result, and you can have something that comes out of a 0 as a result. Alright? We could have something negative over negative, but I don't want to cover that yet. I'll be covering that in the future. Alright, but these are not rational numbers. Which leads me to the segue of what is an irrational number. So we'll talk about the set of irrational numbers. I'm going to do this in set builder's notation again, and again, so you can see how set builder's notation works. I'm going to be translating the set, alright, the set of values x such that x is not rational. And that's pretty much it for irrational numbers. Anything that doesn't go like P over Q such that P and Q are integers and Q cannot be 0 is an irrational number. Alright? So let me write this out, expand this set builder's notation out and translate it. The set of all values x such that x is not rational. And of course I'm assuming in the English language for negating rational we do irrational, right? That's one of those funny words. So let's do examples of irrational numbers to see what's going on. Alright. So we know we can't do any P over Q business where P and Q are integers and Q can't equal 0. So one thing that comes to mind first and foremost is the constant pi, which as far as I can remember goes like 3.14159. For those of you watching that know anything about the constant of pi, you should know that this is a non-repeating, never-ending decimal, in that this decimal keeps on going, it doesn't stop. Alright? There are no two numbers that repeat. And this is me rounding up this decimal place to a certain place value. Alright? And place values is something we'll cover in the future. So that's one irrational number. And I should have written examples of irrational numbers right here. The square root of 2 is an irrational number. There's no way you can get or express the square root of 2 in the rational number format. I think this is, well, I don't remember what it is actually. For those of you with calculators, you can go quickly on your computer calculator. You can see it's a non-repeating, never-ending decimal. Square root of 3 is another irrational number. Square root of 2 over 2. This is irrational. Something like square root of 7 over 5. That's irrational as well. Why? Because we have the numerator, alright, in each of these fractions being irrational numbers themselves. Alright? Because we have those numbers in the numerators that violate the rules of a rational number, that automatically bins it into the irrational number category. Okay? And you can sit here until the cows come home, giving all of these examples of what an irrational number is. Now, I have to mention that not every decimal is irrational. Okay? So, for instance, 1/3. This comes out to 0.33333333333. This is a repeating decimal, right? In fact, you were probably told at some point to write it something like that. Write 2 3s, write a bar over it. This bar over the 2 3s means that we essentially have a repeating decimal, right? And you can even do the same with this if you wanted. Don't have to. Alright, this is kind of obnoxious, actually. But we can see right here that this is a decimal that stems from a rational number. Alright? Irrational numbers give non-repeating, never-ending decimals. Alright? rational numbers like a quarter give decimal values just the same, and we'll see in the future how we achieve these decimal values from these fractional values rather than just our common knowledge. Okay, you know, so we can have rational numbers that come in decimal format. So I just want to say that these are rational. Now, as with everything in math, there are multiple ways of looking at a certain sort of topic or a certain idea. So one thing that I've done is I've given you ways of building sets. Alright? And in particular, I was giving you several number of ways to build sets of the real number system, right? Now, rational numbers, if you think about it, can be comprised of a set of natural numbers, a set of integers, say odd and even integers. I don't know. To be honest, in this tree diagram, which is what this is kind of called, because from the real number system we branch off to rational numbers and irrational numbers, and then from there we branch off onto other stuff. This kind of bit right here is redundant, but we can express all these and physically list them out in sets if we wanted, using this roster form where we establish a pattern and do this dot 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 business, or you know, using this set builders notation, alright, like I've done right here. But another thing we like to do in math is we like to illustrate, if you will, and kind of give a visual of the ideas we've just listed. So another thing I want to introduce to you right now is the so-called real number line, which in and of itself is fairly useful when we're dealing with real numbers. By the way, there are other number systems in addition to the real number system that are available to use, but mostly, you know, the layman's experience and most of what we use is the real number system. I don't know why it's called the real number system as opposed to other number systems out there. Maybe someone can do some research on that and look it up. At some point in the past, some mathematician said, I'm going to call this, or we're going to call this, the real number system. And someone, maybe a bunch of people, mathematicians at the time, decided on that name. No matter, it doesn't really matter the name, but attaching to the name that everyone uses in the community to what this name actually represents, and making that connection and knowing what we're talking about, that's actually very important. So the real number line, I'll just say, is kind of a sort of an illustration of the real number system, and it provides some order to be used in other areas of math. And I'm going to say basic mathematics. Now, this is certainly true, but I have to take aside to mention that this stuff, what I'm doing right here, these fundamentals are extremely important if you want to further your studies in the sciences, particularly, of course, in mathematical-based sciences and engineering. The